Hello, this is Dr. Perez recording the lecture for today. The topic for today is input analysis and arena input analyzer. And as I mentioned in class, now that you're working on your project and probably that you have already some data collected, the question is how are we going to use this data? So that's the question that we are going to try to answer today with this lecture. And But before we get into the details on how to use the data, we need to understand some concepts, and those are the ones that I'm going to explain now. So we're gonna briefly talk about these four things. Well, the first three things are hypothesis testing, p-values, and square error. And the reason I'm going to explain them is because these are the three concepts that we're going to use to decide whether or not our data is fitting a probability model that we can use in our simulation. And then finally, I'm going to teach you how to use the Arena Input Analyzer from Rockwell Software to perform the analysis very fast and easy. And that will allow you to use the information into your simulation model. So first, let's briefly talk about hypothesis testing. And basically, hypothesis testing is a statistical decision making tool or methodology where two complementary hypotheses are formulated. One is named the null hypothesis, which is then denoted by the HO symbol, and then we have the alternative hypothesis, which is denoted by H1. Then a decision is applied to the null hypothesis, which is either accepted or rejected. So we're going to formulate an hypothesis and we're going to decide whether or not this hypothesis is accepted or not based on an output from our analysis. Consequently, two types of errors are possible. Type 1 error is rejecting the null hypothesis erroneously, and type 2 error is accepting these null hypotheses erroneously, meaning that we are saying that H0 is true when in reality it's not true. So the goal of hypothesis testing is to reject H0 or the null hypothesis such that if H0 in fact is true, then the probability of erroneously rejecting H0, which is the type 1 error, does not exceed some prescribed probability alpha called the confidence level or the significance level. So our goal with the hypothesis testing is that we want to reject this H0, okay? And such that if the hypothesis is true, we have a very small probability of error of rejecting these null hypotheses. So the smaller alpha is, the higher is the confidence in a corresponding rejection decision. So suppose we wish to compare the failure rate of two machines. Okay, and those are denoted by these delta values, delta 1 and delta 2, of machine 1 and 2 respectively. And this is a test that is performed at significant level of 95%, which means that alpha is 0.05. So the associated hypothesis followed these two. So we are saying that our null hypothesis is saying that the failure rates of the first machines are less than or equal to the failure rates of the second machine. And our alternative hypothesis basically is a complement, which is saying that the failure rate of the first machine is greater than the failure rate of the second machine. So the modeler forms a test statistic, T, from some observed data with a known distribution on the null hypothesis. Okay, so the state space S of T is then partitioned into disjoint regions, which are separated by the area or the probability for each one of these hypotheses. R0 is going to represent the area of the acceptance region, and R1 is the region for the rejection region. such as the probability of type 1 error does not exceed this alpha 0.05. So in practice, the analyst is going to compute the realization of t, which is it's coming from this t distribution, and decides to accept or reject A0 according to as t fell in the region R0 or R1 respectively. Okay, so that's again is a quick review in terms of the hypothesis testing. Now I'm going to proceed and explain a little bit about the p-value, which is an alternative approach to hypothesis testing. And in here we compute the probability value or the p-value of the realization of the test statistic t, where p is the smallest significance level for which the computed test statistic t can be rejected. So in hypothesis testing, we fix alpha and then decide whether to accept or reject depending on the region in which the test statistic fell. Conversely, suppose we does not fix this alpha value before computing the test statistic, but we allow it to float. We would like to know how small can this alpha be made and still permit that the null hypothesis to be rejected. This means that we seek the smallest alpha that rejects a null hypothesis. Okay, then as I mentioned, this is an alternative approach to hypothesis testing. The p-value contains a considerable amount of information on the quality of our test decision. Decide whether to reject the null hypothesis or accept it, but we can also obtain an idea of how strongly we reject or accept this hypothesis. So the smaller p is compared to alpha, the stronger is its rejection. Okay, so the smaller the p when compared to alpha, the stronger is its rejection. Conversely, the larger p is relative to alpha, the stronger is its acceptance. And this is one of the numbers that we are going to use to decide which probability distribution fits better our data. So in terms of the best fits, p-value for the test statistics is a measure of fit. The larger, the better. So a large p-value means that we have a good fit for our data. However, a small p-value signifies that we have a poor fit for our data. Many software packages use p-value as a ranking measure to automatically determine the best fits, and that is the case also for the input analyzer. But we need to be cautious about two things. The close conformance to the data does not always lead to the most appropriate input model. Okay, so that's one thing. And p-value does not say much about where the lack of fit occurs. So as a recommendation, always inspect automatic selection using graphical methods. And this will make more sense when we start looking at the use of the software. So now I want also to review the meaning of the square error. So the sum of the square discrepancies between histogram frequencies and the fitted distribution frequencies. So this is the meaning of the square error. And from your basic probability course, you remember that we can develop histograms. These are the graphs, the bars, bar graphs that we can basically map to our data by looking at the frequencies in terms of how many of my data points are within a interval. And again, this is a bar graph that is used to look at the shape of the frequencies of our data points. And using those histograms, we can find the square error. So again, it's the sum of the square discrepancies between histogram frequencies and the fitted distribution frequencies. It provides a measure of the goodness of a distribution to an empirical data set, and it is computed using this formula, its square, where J is the number of cells in the histogram, P hat J is the relative frequency of the J cell in the histogram, and Pj is the theoretical frequency. Okay, so that being said, we can now look at the use of the software. Again, this is the Arena Input Analyzer, and this is one of the tools that is provided by the Rockwell software, in addition to the simulation package, the Arena. Okay, so in order to use it, as I mentioned, this is a separate application, also via the tool menus in Arena. And the Arena Input Analyzer functionality includes feeding a distribution to a sample data. The user will have two options. Um, Specify a particular distribution and request the associated parameters that provide the best fit, or request both the class of distributions as well as the associated parameters that provide the best fit. And here's the list of the Arena supported distributions and their parameters. So these are the distributions that we can fit to our data. So the list includes the exponential, the normal distribution, the triangular, the uniform, the Erlang, the beta distribution, the gamma distribution, the Johnson distribution, the log normal distribution, the Poisson, the Weibull, the continuous, and the discrete. So far in class we've been using some of them. Again, in the exercises that we have been doing in class, I've been providing you with the information before, on the tests that you are using to build your models. But the idea now is with your project is that you can generate these distributions so you can represent what's happening in your project. Okay, so we're gonna find out for your data, for the data that you are collecting, for example, for the interarrival times, for the processing times, for mostly those two, what is the best distribution that describes the performance of your system? So assume that you have a sample data that is independent and identically distributed, IID, a list of observed values from the physical system, and that's the list that you are generating for your project. We want to select or fit a probability distribution for use in generating input for the simulation model. So for example, if I want to fit a distribution to the following data, um, I'm going to show you how to do that in a second. So let me show you something else. So first, in order to find the Arena Input Analyzer, you can go to the Start menu, and on Programs there will be Rockwell Software, and under the Arena folder you will see the Input Analyzer. Okay, so you can click there and this is what you're going to see. But before we get into using the software, I want to show you something else. So this is the files that I have uploaded for today's lecture. There's a PowerPoint file, which is the one that I'm using for the lecture today, and there's an Excel file. This Excel file basically contains the information that is presented here in the PowerPoint. Okay, so the idea is that you are going to collect some data from the system and you're going to tabulate it in a way like this one, so we can use it for our input analyzer, and then we can fit a distribution to your data. So in this particular case we have 100 data points, okay, and this can represent something like the interarrival time, so meaning that the first customer arrived 12 minutes after opening the store, and then the next one arrived 20 minutes after the first one, and then the next one arrived 30 minutes after the second one, and then the fourth one arrived in 17 minutes after the third one, and so on. Okay, so that's the idea for the inter-arrival times. So let me open this a little bit. So once you have your data tabulated, we can use this information to fit a probability distribution. Okay, so what I'm going to do now is I'm going to use this Excel file, and I'm going to put it in a in a format that can be used by the input analyzer. So as you can see here, there's nothing different. This is the typical way that you will input numbers into Excel, but now I'm going to save this file as a text file. So let me find, okay, so now I'm going to use this data file, and I'm going to find text. So I'm going to use the format text space delimited, and I'm going to save it. Alright, Excel is going to ask me if I want to keep it. I'm going to say okay. Do you want to keep using this format? I'm going to say yes. So now if I go here, I don't think that was the right file. Sorry. Let me delete this. Okay, so it says that we are using that right now. So let me see if I can erase that file from here. Yes. Okay, so I'm going to save this one more time. Thought I was using the right format, but I wasn't. So I'm going to use text tab delimited now and see if this one is going to work. Okay, yes, yes. So if I go to input analyzer and I open this one, this is what I was looking for. Okay, so if you save it using the tab delimited text format, you should be able to open the file afterwards, and it should look like this one. Okay, so let me guide you one more time in how to generate this file, because this is a very important step. So I need to save this. No, I'm gonna save it as Excel. Yes. Okay, so I'm going to delete that file one more time. So you'll go here, File, Save As, find the location, and you're going to look for Test, tab delimited, use that one, click Save, hit OK, yes, and again you should have your file generated in this form. So what I'm going to do now is I'm going to use this file as an input for the input analyzer in Arena. Okay, so I'm going to open Arena now, and the steps that you need to follow are the following. So you're gonna go here and you're gonna click here in New, and that's going to open this window. Then you're gonna go to File, Data File, Use Existing, and you're gonna find that file that we just saved. So let me find that one. In order for you to see it, you might need to change the file type here to text files, and you will see the file now. So you can click on that one, and it will open and it will generate this frequency histogram for you. Okay, so now I have my data. This is a histogram, and you can see the information here listed at the bottom of the histogram. So we have 100 data points, we have a minimum value, maximum value, the mean, and the standard deviation. And we are using 10 intervals to fit or to develop this histogram. So what I want to do now is, okay, I have my data. I want to know now what is the best distribution that can fit this data. So for doing that, we have multiple options. There's a fit menu here in which you can choose which distribution you want to fit. But my recommendation is to use this fit all distribution, because what the software is going to do is going to show you what is the best fit for your data. So if you go there, in this particular case, the software is saying that the best distribution is the beta, and it has this expression generated for you. So that is the expression that you are going to use in Arena when building your simulation model. So what I'm saying is, if for this case, the data that I was trying to fit a distribution was my interarrival times, meaning that the times that my entities are arriving to the system, if that was the data that I was using, I can use this expression to um, generate my entities in Arena. So that will means that will mean that I'm going to use this in my create block. So I'm trying to see what's going on. Where's the software? Okay, so it's kind of hiding from here. Let me try to open it again. Okay. So that means that if I want to use a create block, I will use this I would use this expression right here. I would copy it, and since again I'm assuming that data is for my interarrival times, I can use that distribution here. So I'm going to use expression, and my expression is going to be that information, the beta. And if this is in minutes, and then I will close it. Okay, so the idea is you're using the data that you're getting from your system, you are fitting a distribution to it, and then you're using it in your simulation model. Okay, so going back to the input analyzer, let me show you something, a couple of things from here. So using the fit menu and upon selection of a particular distribution, the input analyzer provides a graph of the best fit distribution, the parameters of the best fit distribution, the statistical outcomes of the goodness of fit test employee, and the information and the summary information on the empirical data and histogram constructed from it. So before I forget, when I say what is the best fit, you can see that initially we didn't have this line there, right? Well, that line is the line that is representing the fit of the beta distribution. If I choose a different distribution such as the exponential, you will see that that line is going to change. It's going to look a little bit more as the exponential distribution shape, but that shape is not close to the shape that we have in our data. So that's why when you do fit all, it's going to find the probability distribution that provides the best fit for your data. And a couple of things in terms of the summary, you will see that the software is providing you with the p-value. Okay, so here you go. And again, as I mentioned earlier, the p-value is the statistic methodology that is used by the input analyzer to decide which probability distribution is the best. And as I explained earlier, the larger the p-value, the better the fit. So for example, here the chi-square test is telling me that the p-value is greater or 0.412, and the KS test is telling me that the p-value is greater than 0.1015. If I change the distribution, let's say to the exponential, you see that the p-value will go down, which means that this is not a good fit for our probability distribution or for our data. Okay, so again, the beta distribution is the one that provides the best fit, and as a rule of thumb, a p-value that is greater than 0.05 provides, or if your fit provides you with a p-value that is greater than 0.05, that means that the fit is good. And we discussed that here in the slide. So this is the exercise that we just performed. Again, this is just giving you the instructions step by step. So this is the exercise that we just completed. In terms of the fit menu, it fits the distribution, does the goodness of fit test for you, fit a specific distribution from plus density over histogram for visual tests, and give the exact expression to copy and paste over into the simulation model, which is what I did. Remember, I copied the expression and I used it in my create block. And this is the point that I wanted to touch on. So this second point here gives results on goodness of fit test. So the most important part is the p-value, and it is always between 0 and 1, and a small p-value means that it's less than 0.05, and that means that you have a poor fit. So my recommendation at that point is to try it again, get more data in order for you to see if your fit can improve, or I will not give up even though I listed here, but give up in the sense that we might need to go and get more information from the system. Okay, so if you get a p-value that is greater than 0.05, that means that you're finding a good fit for your data and you're good to go, and you can use that information in your simulation model. So here's the fit all of a Reno theoretical distribution. So this is the fit menu. So if you want to fit them all, you can also do that. And what that's going to do, if we go back to the input analyzer and we go to the fit all menu, it's going to give you the best distribution. But if you choose this icon here, this icon right here, fit all summary, is going to give you the list of the distributions that fit the best to your data. Okay, so again, the best distribution in terms of the square error is the beta distribution, and then follows the uniform, then the normal, and then the Weibull. Okay, so the best fit for this case is the beta distribution. You can also fit an empirical distribution, and this is for the case in which you have no other options. So the empirical distribution can be used when theoretical distributions fit poorly. And finally, the last thing that you can use with the input analyzer is to generate data. So in the case you want to generate some data that follows a specific distribution, you also have that option here for the input analyzer. But for the purpose of this class and the purpose of the project, that's not going to be a tool that you're going to use. Okay, so that concludes this lecture. And again, the idea is for you to use the data that you're collecting from your real system, and you put it in the right formats and we can find a good fit for it. And if you find a good fit in terms of a probability distribution, you can use that fit as an input to your simulation model um, to model your system. Okay, so that concludes the lecture. And if you have any questions, you can send me an email or we can discuss in class next time. Thank you.